Hello everyone, and welcome to the next session of Live Coffee Talks, which is presented by the Azure for Technology Partners program, and which is designed to help partners in migrating to Asia while providing free of charge business and technical assistance. It also helps to market your SaaS and PaaS offerings for Microsoft's commercial marketplaces. I would like to remind you that these coffee talks are held by Don Daniel, and if you want to keep track of the upcoming events and not to miss the one you need, you can subscribe to the updates of our social networks on LinkedIn, YouTube, Facebook, and Vimeo. And you can also follow our page, and you can also join the program by visiting hp.dom-daniel.com. And of course, if you have questions during or after my presentation, feel free to leave them on the chat or comment section of any of the above-mentioned platforms. My colleagues and I will answer them as soon as possible. Alternatively, you can email me your questions or message me on LinkedIn. Now, let's move on to our topic. Today, I will be talking about a new programming model of durable functions, durable entities, also called stateful entities, and which are very much like the virtual actors model. On today's agenda, I would like to give you a quick introduction to Azure functions and durable functions, with briefly discussion on durable functions, different patterns, while taking into consideration the aggregator. We will also examine the actor model and the characteristic of actors, and smoothly pass over to durable entities as one of its brighter implementation. Furthermore, we will also discuss the pros and cons of durable entities. After that, there will be a demo, and as a final point, we will compare virtual actors and durable entities. However, before passing to durable entities, let's quickly remember what are Azure functions. So we have events which react and get inputs from growing list of services. These events can be blob triggered, Cosmos DB triggered, whatever it is. And these, in this case, are triggers and input bindings. And it is going to run some code. And probably we have output that is sending result to those list of services. And in this case, these are our output bindings. The important thing here is that Azure functions are stateless. They run for some time, and when they are done, they are just gone. That is, you don't control where and when function instances are provisioned or deprovisioned. There is no way to store data between requests reliably within the process, and in this case, an external storage or cache has to be utilized. However, if you want to work with state, you must use something else, and this can actually be durable entities. Durable functions are stateful functions in a serverless environment. These are extensions on Azure functions. That is, they use the Azure functions programming model. These durable functions can basically create a stateful workflow functions. So you can chain different functions together, get the output of one function as the input for another function, and thus creating a workflow. And Azure durable functions are built on top of the durable task framework, which is an open source library. As Azure Functions is the serverless evolution of Azure Web Jobs, Durable Functions is the serverless evolution of Durable Task Framework. So at first, let's remember the main components of Durable Functions. Those play a vital role while working with Azure Durable Functions. The first one is the orchestration client. It starts and stops the orchestrator functions, and it takes the responsibility to monitor them. When you are creating an HTTP triggered function, initially, you can call that HTTP triggered function as the orchestrator client. This is responsible to get the request, and then it starts the orchestrator function. So this is the first step in the whole process. The next one is the orchestrate function, and it plays a major role while building the durable function and orchestrate function. It is considered to be the heart of the workflow in code, and in this function, you need to write workflows. You can call the activity function from the orchestrator function inside the code. You can also call another orchestrator functions and also sub-orchestrator functions from the main orchestrator function. The third one is the activity function, and activity function is called as the basic unit of durable function that executes one task at a time. You can call many activity functions inside the orchestrator function, and as each one of the activity function executes only one task. And of course, the last one is the entity functions. Just to mention, don't worry if some of the concepts mentioned are not clear at this time. I plan to demonstrate all these concepts at the end. So there are a lot of stateful patterns in durable functions that allow developers to implement in a serverless environment. We have function chaining, we have fan-out, fan-in, async HTTP API, monitor, human interaction, and the last one is the event aggregation. Today I'm not going very deep into these patterns because the goal of my presentation here is durable entities and the aggregator pattern, as it is the pattern that we can use with durable entities. Let me just inform you that we have already discussed these different patterns in our previous live coffee talks, and if you are interested in learning more about them, you can just visit atp.dom-daniel.com to find the subject you need. And you can certainly check the documentation which gives a thorough description of each of them. This aggregator pattern actually allows us to have a lot of messages in an entity, and this entity will do all the serialization. It will serialize and process each message. All the time, it just aggregates all these messages. Like an event sourcing pattern, it just processes all the messages, and at the end, we have the complete state of the entity. The problem about trying to implement this pattern with stateless functions is that concurrency control becomes a huge problem. You should not only worry about multiple threads modifying the same data at the same time, but you also need to be sure that the aggregator is operating on a single virtual machine at a time. And durable entities allow you to easily implement this pattern as a single function. So, as durable entities, and this aggregator pattern was modeled using something like actors. At first, let's have a look at actor model. The actor model in computer science is a model of concurrent computation. It treats actors as the universal primitive of concurrent computation. In response to a message that actor receives, it can make local decisions, create more actors, send more messages, and determine how to respond to the next message received. Actors may modify their own private state, but can only affect each other indirectly through messaging, also known as signaling. However, in virtual actor model, every actor has a unique identity, which is a GUI ID. Actors are isolated, that is, they do not share memory. Thus, two actors can interact only by sending messages. So now let's move on to the characteristics of actors. So an actor is always addressable via an ID. Each actor will have its own ID. It is also a state machine, so that each of the actors are in a specific state. They communicate through async messages. It is very lightweight, like every actor is a lightweight state, and they are just represented in a lightweight manner. It does not share its global state, and each actor owns its own private state. That is, one actor does not know about the other actor. When we send a message, each message is processed one at a time in order. So if I send a whole bunch of messages, it will process each one in a time. This is very important, for example, if we have financial data or something like that. And the last one, it is always a single-threaded object. And this is certainly important because we have processed one message at a time. So this is why it is a single-threaded. It has one thread and does everything under that thread. And this actually makes sure that you will always have the latest state. So entity functions is a recent addition to Azure Durable Functions. However, this feature is only available in Durable Functions 2.0 and above. Entity functions define operations for reading and updating small pieces of state, known as durable entities. Like orchestrator functions, entity functions are functions with a special trigger type, and it is the entity trigger. Entities provide a means for scaling out applications by distributing the work across many entities, each with a modestly sized state. An entity can be anything like a hotel, a book, a store, etc. Now let's have a look at characteristics of our durable entities. As we have said, durable entities are very much like actors. It's not completely the actor model, but it is very much like the actors. So durable entities are addressable via an entity ID. One attraction here is that durable entities give us an easy way to store state without needing a persistent storage. However, they are not equivalent to a storage, that is, they are not a replacement for a storage. Certainly, if you have minimal carrying capabilities, you can look up an entity by ID, and you can ask for all entities of a particular type. However, anything you need rich and powerful carrying capabilities for still belongs in a persistent storage. So they manage their state, and we don't have to know how to implement this actor model ourselves. This has completely implemented for us so that we can just use it. Another consideration here is that entity state is deserialized and reserialized to JSON every time the entity is messaged. So you probably also want to avoid entities that manage very large amount of state. And once again, we are working with durable entities which store all in the table storage. We can actually go to our table storage and check what is the status of our actors, and in this case, in our case, of our durable entities. And it is represented in JSON, and we can see all these properties in the table storage. It executes serially. Hundreds of thousands of operations will be executed serially one at a time. When not executing operations, entities are silently unloaded from memory. So when we are not working with a specific entity, it will unload it, will place it into the table storage, and only when we call that entity again, it will actually get it from the table storage and will load it into memory to work with it again consequently. For now, let's look through a few examples where durable entities have been a good fit for a problem. So the first one is a circuit breaker, which is a commonly needed pattern in cloud architectures used to temporarily pause an activity that is repeatedly failing. The circuit breaker is actually a simple example of a state machine, which is a very helpful pattern that can be applied to many problems in software development. One idea that the Azure Functions team shared was of using durable entities to detect when an IoT device was offline. This model can also be used with short-lived entities, like some counter. This can simply be done with entities rather than having to have a running count maintained in a persistent storage, and thus resulting in unnecessary storage load and the need to consider the concurrency. One usage which I have experimented with entities while using them in combination with durable functions in our company is for working with conversations. Each message in a conversation is stored as an entity, and the conversation itself is an entity, and so forth. And consequently, here are some problems where durable entities is not a good choice. So, durable entities in any way should not replace orchestrator functions as the preferred approach for building serverless workflows. Orchestrations are a great way of expressing a workflow that has a clear pathway from beginning to end. As I have already mentioned, one of the advantages of durable entities is that they give us an easy way to store state without needing a persistent storage. However, they are not a replacement for storage, and for anything that require rich and powerful carrying capabilities, storage is a good choice. And it is possible that you may expect to be able to call your entities remotely. In other words, you send an entity a message, it processes it, and then it returns the new state to you all in a single operation. However, this is not supported. Durable entities follow a pattern similar to CQRS, where you can either update state, that is by sending a message, or query for state, that is requesting the current state, but not both at the same time. Now with that said, let's go to the demo. So I'm going to show a simple movie ticket booking project. For my demo, I will be using a C#. So let's open Visual Studio and create our Azure Functions project. Let's create a new project. From the templates, let's choose the Azure Functions template. Next, let's give a name for our Azure function. Select the location. Let's choose the desktop. And the solution name is already filled. Then create. As I have mentioned, the durable entities are available from the durable functions 2.0 version and above. But for now, let's choose .NET Core 3. Here are different Azure Functions trigger types. You can choose an empty template. You can choose timer trigger, queue trigger. There are a lot of. But for now, let's choose durable functions orchestration. As the durable functions extension uses an Azure storage account behind the scenes to track the state of the orchestrations, we need a storage account. You can use your storage account, or for now, as I'm working locally, I will use the storage emulator. And now, as we have chose the storage emulator, we can create our Azure function with durable orchestration template. Let's wait a little bit. So here is our durable function, and you can see a simple sample have been generated from the template. So let's look what's going on here. We have the orchestrator function, here our orchestrator function with the attribute orchestration trigger, which come with the extension. And from the CS profile, we can see that it is already installed the durable task extension for us. And if we go back to our orchestrator function, we can see that here we have the context, the durable orchestration context, which comes with the extension. And this context object allows us to call another functions by their name and by giving the input. And here are our inside the body of the orchestrate function. We can see that it is calling activity functions. The activity function here is the function one hello. What does this call activity async is doing actually? It is dropping a message in a queue, and some VM will pick up that message and will run that say hello activity, and it will process it and return some value. And here we see the await keyword. The orchestrator here actually goes to sleep. While say hello is running, the orchestrator is sleeping. When the activity finishes its work, it sends notification to an orchestrator with the result. Behind the scenes, we are actually persisting the state. When the orchestrator wakes back up and wants to call another activity, that is the second activity, it will look up in its history invocation list to see whether it executes that activity or not. And if it has done, it will pass to another one. So here we also have the starter function, which actually starts the orchestrator function, and the orchestrator function, which starts the activity functions. So now let's move on to our entities. As there isn't enough time left, I will show you the implemented version of our movie sample app. So now let's go to our movie application. Let's wait a little. Well, it has already loaded. So here we have starter function. That is our movie client function, which starts the movie orchestrate function. We have one activity function and a lot of entities. The movie entity, the room entity where the movie will go on, and the screening. Here are, I will show here the models. And so this is an implementation of the movie entity using classes and methods. And let's go to the movie entity. The state of this entity is an object of type movies, which contains a field that stores the current value of the movies. The movie itself is a C# class. It has ID, title, and playing at field where playing at field. To persist this object in storage, we serialize and deserialize it by the JSON.NET library. So this movie entity offers 4 operations: add, create, add, does movie exist, and get movies operations. The run function here is required for using the class-based syntax. It must be a static Azure function, and it executes for each operation message that is processed by the entity. When this dispatch async movies entity is called, and the entity isn't already in memory, it constructs a movies entity object and populates its fields from the last persisted JSON found in the storage, if there are any. And then it invokes with the matching name. So in order to access the entities, one-way or two-way communication can be used. One way is calling an signaling, and it is waiting for a response. One way is calling an entity, and it is waiting for the response. Signaling in the entity uses one-way communication. You send an operation message, but don't wait for a response. To access entities, I have used standard Azure functions with the entity client binding. Here it is. So now I will show it. Here is the create movie function. You can see here the durable client binding, and all it is doing, it takes the movie entity ID, and here we are just assigning the entity with the movie entity ID, and we are just calling the operation and giving the operation input. We can run the project to test it for now. So here we can see that the Azure function runtime gives us URLs for every function. For the first step, let's create a movie. Let me just copy the URL, and for request I will use Postman. Let's pass the URL here. It will be a post request. And let me just insert some values. Let's choose the JSON and pass some values. ID, let's say 1. The title of the movie. And the room where the movie will be played. So let's write the room, for example, number 1. So let's send the request. Here we can see that we have got 200 OK. That is, the request was successful. Now we can go and get the results for the function, for the movies entity function. Let me just pass to another project. Here we have get movies by ID function, which again takes the entity ID. And here we are not calling, or signaling, we are just reading the entity state with read entity state async, and just passing the entity ID. So now let's copy the URL for this function. Let's go to the Postman, pass the URL and the one, and send the request. Here we see the result, the ID, title, and the room. With get movies function, we can, but before taking all the movies, let's first of all create some more movies. The request is not going. So let's wait a little bit more. It seems there is a problem with connection. The problem was that the console was stopped. Now we can add more movies. And the last one. Now we can actually get all the movies. So let's pass the URL and send a request. So let's wait a little bit more. Now we can see that our function get all movies returned all the movies for the movie entity. And the last thing, for my demo, let's go to Storage Explorer and see what was happened behind the scenes. So, as we are working locally, we have used the Azure Storage Emulator. Again, we have a problem with connection. Okay, let's go to the tables. And here we have two tables. Actually, these are task hubs, and the name of the task hub is configurable from the code. You can, if you don't want to leave the default name, you can just configure it in host.json file, which I can show now. Here it is, the durable task and hub name, the preferred hub name, which you choose. So the first one, the second one, sorry, is the instances which were created for the entities. Here we see the entity name and the key. And if we click on this entity and go to the input field, here we can see all the results which are persisted in the storage. This table is responsible for the orchestrator, that is, and not only orchestrator. It is persisting the history invocation of orchestrator functions, entity functions, and activity functions. Here we can see that the orchestrator started, it executed our entity, and after that the orchestrator completed. So this was all for my demo, and as a final point, I would like to compare virtual actors to durable entities. So durable entities put durability over latency. That is, they may not be the best option for applications that require strict latency. There is no built-in timeout for messages for durable entities, and unlike virtual actors, where all messages time out after a configurable time. Messages sent between entities are delivered reliably and in order. In virtual actors, reliable or ordered delivery is supported sending content through streams, but it isn't guaranteed for all messages. An entity's request response patterns are limited to orchestrations. Only one-way messaging, also known as signaling, is permitted from within entities, is in the original actor model, and unlike virtual actors. The next one is that durable entities don't deadlock. Virtual actors can deadlock and don't resolve until messages time out. And the last one, durable entities can be used in conjunction with durable orchestrations and support a distributed locking mechanism. This was all for the coffee talk. Thank you for your attention. And if you have any questions, you can leave them on the chat and I will try to answer them. You can also message me your questions on LinkedIn, or you can email me. So let me check, are there any questions? So it seems there are no questions. So thanks everyone for staying with me during this coffee talk presented by the Asia for Technology Partners program, and which is designed to help partners in migrating to Asia. Let me remind you that there are many coffee talks ahead, so please don't forget to follow us on social media to get updated on the latest coffee talks. Once again, thank you for joining me, and goodbye.